Bit masking is a powerful and flexible mechanism offered by Unigine to apply or enable certain effects or features to objects selectively. The principle is as follows. Various effects use certain sets of flags, bit masks, to define their scope. Entities, such as cameras, objects, collision shapes, etc., contain some of these bit masks, depending on entity's type and applicability of the effect. The masks are compared bitwise using logical conjunction, which means the first bit of the first mask is compared to the first bit of the second mask, and so on. 2-bit masks are considered matching if they have at least one matching bit, regardless of the values of other bits. So, an effect is applied to an object or takes it into account only if required masks match. This mechanism is pretty useful in optimization. You can limit real-time shadows, reflections, physical interactions, and other effects by dividing all objects in the virtual world into separate groups and configure certain effects and features for them. In this tutorial, we'll consider various types of bit masks available and give some tips on how to use them. The viewport mask, which belongs to camera settings, enables you to display objects in the camera viewport selectively. Click the mask button to configure it. In the pop-up, you can see a hexadecimal representation of the mask intended for copying the mask's value to another mask, and the binary pattern represented by a set of 32 bits. You can toggle each of them on and off, thus defining the mask. You can also tag a certain bit by setting a name for it. By default, all objects in the scene have the first bit set, so we can call it scene. An object's surface is rendered in the camera's viewport if its viewport mask corresponds to the one of the camera. Let's select all the surfaces and disable the bit called scene. The object became invisible, but it's still there. We can see its shadow cast as usual. Let's reserve a special bit for the car. This approach enables you to make different objects displayed in the viewports of different cameras. We'll just need one more viewport for it. The second viewport has its own scene camera, different from the first one. Now it's easy to make the car invisible, only the shadow remains the same. Let's use another bit of the viewport mask for another object. And now we can hide it from the first camera. We can disable the Cast World Shadows option to get rid of inconsistent shadows and leave only the ones provided by the Screen Space Shadows effect. The viewport mask is available for materials as well, enabling you to manage rendering of multiple objects that have the same material assigned. Any surface is visible by default because its viewport mask and the viewport mask of its material match the camera's one. The viewport mask can also be used to selectively display reflections baked in an environment probe. Let's make this info tooltip invisible in the reflection on the floor. The probe has the reflection viewport mask defining what should be baked into the reflection. By default, the probe reflects all geometry, so we limit the mask only to the scene bit. After that, we change the viewport mask of the text and the arrow icon to make it different and bake the reflection. Now the baked reflection does not include the tooltip. One more use case of the viewport mask is dynamic reflections. For example, the planar reflection doubles the polygon count since it takes into account all geometry in the scene by default. This may cause a performance drop for such a heavy scene. To simplify rendering of a reflection for a certain object, you can prepare a model with one additional simplified level of detail to be used for reflection. Let's define one bit of the viewport mask for it, and another one for the surfaces of the car to be displayed. Next, we need to hide the low poly surface from the camera and exclude the high poly one from reflections by adjusting the reflection mask. The next step is to adjust the mask of the reflection provider, the plane with the planar reflection effect enabled. Switch to the Parameters tab and set up the viewport mask. We need only the low poly one to be reflected. Here it is. A single poly LOD of the car is taken into account by the planar reflection, which is rendered much faster than before. Although there is a problem. The car seems to be unlit, so let's add the world light to the reflection too. Reflection of all surroundings can be produced by a less consuming method, screen space reflections. Enable the SSR feature in the Rendering Features section to make the reflection more consistent. By using the shadow mask, you can control shadow casting by a surface lit by a light source. Using a simpler LOD is also a common way to reduce shadow rendering load. The shadow of a surface from a light source is rendered if shadow masks of the surface and the material assigned to it match the shadow mask of the light source at least one bit. The workflow is the same as for reflections. We make the low-poly surface invisible and use it to cast shadows, while disabling shadow casting for all other surfaces by unchecking all bits of the shadow mask. The shadow is cast by a low-poly model now, which is accurate enough and not so hard to compute. By default, decals are projected onto all visible objects, like this road marking projected onto the tank. You can change it via the material mask in the material parameters. It's a 24-bit mask that specifies materials to be affected by a decal. A decal can be projected onto an object only if the mask of the material assigned to it corresponds to the material mask of the decal. If the masks do not match, the decal does not affect the object. Have a look at this tank. Intersections are essential for all 3D engines and are used very often, ray casting, etc. You can also detect them selectively to improve performance. In this example, we use a script function to display a wireframe for an object that is currently under the cursor. In your script, you can use a certain bit mask and compare it with intersection masks on surfaces to filter some of them out. Intersections for surfaces with non-matching or disabled intersection masks won't be detected. Now you can see that intersections with the doors and the tube, the masks of which we've changed, are being ignored. Calculating intersections can take a lot of time and significantly affect performance, especially in projects with a lot of geometry and sophisticated logic. Therefore, a great way to increase performance is to use bit masking and low-poly models for intersections. Intersection mask can also be used to cut out grass in areas of intersection with certain objects. To specify such objects, you can use the cutout intersection mask of the grass. For example, let's create a spherical primitive and make its surface and shadows invisible via the corresponding masks. Then we enable a special grass cutout bit in the intersection mask and get an empty space in the grass that can be changed dynamically at runtime. Unigen allows you to fine-tune physical interactions between objects. For example, you can enable shape-surface collisions to detect collisions between physical objects with a collision shape assigned, and static geometry, such as this table. This approach allows you to simplify physical calculations as static objects without a body and shape assigned are excluded from physical simulation, but we're still able to detect collisions with them. The collision mask of a physical shape enables you to filter collision detection for particular shapes and surfaces. Only the ones with matching collision masks will collide. If masks do not match, shapes and bodies simply ignore each other by going through. A surface of an object will collide with a shape if collider object state is enabled and collision mask of the surface matches the one of the shape. Let's slow down the simulation a bit and check out collisions with the table. Now, all objects interact with it. But once we change the mask of the shape, now it doesn't match, the cube goes through the surface ignoring it. Collisions between physical shapes are treated the same way. This is a way to define groups of interacting objects in order to simplify physical simulation and improve performance. Another way to make shapes ignore each other is to use exclusion mask. Objects with matching exclusion masks will never collide, even if their collision masks match. The physical mask is a bit mask that enables you to filter objects interacting with physical effects, such as force, wind, and noise. A physical wind object with default settings makes all physical bodies move if their physical masks match. Otherwise, the physical effect is ignored. Every camera has bit masks for sound effects. The sound source mask is used to select sound sources to be heard, while the reverberation mask defines reverberation zones to be taken into account by the camera. If the corresponding mask does not match the one of the camera, neither the sound source nor the reverberation zone can be heard by the camera. For a sound to reverberate, at least one bit of its reverberation mask should match the same mask of the reverberation zone. Sound sources also have the occlusion mask, a bit mask that defines which surfaces occlude the selected sound source. For a sound source to be occluded by a surface, they must have matching occlusion masks and the occlusion parameter greater than 0. Navigation mask is used to specify navigation areas to be taken into account in the process of pathfinding. In this example, there are 2 points and different paths between them. We have found the shortest path using a script and providing the navigation mask as the function argument. Navigation masks of green navigation sectors should match the navigation mask of the route to take them into account during pathfinding. Otherwise, the sector won't be considered. Now, only the second path is found. Obstacle objects are placed inside navigation areas. They should be avoided during pathfinding. Obstacle mask of an obstacle should match the one provided to the script function. Otherwise, the obstacle is simply ignored. Thus, you can tag groups of navigation areas and obstacles. The field mask specifies an area of the field to be applied to grass, water, or clouds. In this example, water fills the inner area of the boat because boat's deck is lower than the water surface. The most suitable way to get rid of such artifact is to use a field spacer object to cut out water in a certain area. Don't forget to toggle on the field spacer interaction with the water material. The field mask of the field node should match the water field mask. Otherwise, they will ignore each other. Proper configuration of bit masks makes even heavy scenes less performance-consuming, while keeping all effects looking consistent and convincing. For more information on bit masking, please refer to our online documentation.